Welcome to the journey of exploring the fascinating history of our planet. This video will guide you through the formation of Earth from billions of years ago, the major stages of its development, and how it transformed into the vibrant habitat we know today. We'll delve into astronomical events, volcanic activity, and the process of life's evolution. Subscribe, like, and share to join us in discovering more exciting facts about our blue planet. Earth, the third planet from the Sun, is the only known place in the solar system that hosts life. Its formation and development spanned billions of years, evolving from a cloud of gas and dust to a planet with climate, oceans, and complex life. This study will detail the key stages in Earth's formation and development, from the planet's birth, the evolution of its crust, atmosphere, and oceans, to the emergence and evolution of life. The formation stage of Earth. Solar nebula stage. The solar nebula stage, around 4.6 billion years ago, was the beginning of the formation of not only Earth, but the entire solar system. Here is a detailed analysis of the process, from a cloud of cosmic gas and dust to the complete structure of the planets. The origin of the solar nebula. The solar nebula was a massive cloud of dust and gas, primarily containing light elements like hydrogen and helium, along with heavier elements such as carbon, oxygen, iron, and silicon. It is believed that this cloud formed from the remnants of previous large star explosions, supernovae, which enriched it with heavier elements produced through nuclear fusion in stars. The collapse of the solar nebula. Under the influence of gravity, the nebula began collapsing inward. This collapse might have been triggered by a major event, such as shock waves from a nearby supernova, creating pressure that destabilized the nebula. As it collapsed, the cloud of dust and gas began spinning faster due to the conservation of angular momentum, leading to the formation of a rotating disk of material around a central core. The formation of the protostellar disk. During the spinning process, centrifugal forces caused the material in the nebula to spread out into a disk shape, known as the protoplanetary disk. The central core became increasingly dense and hotter, eventually forming the Sun. Meanwhile, the rotating disk around the core contained dust particles, ice, and gas, the building blocks for the planets and other celestial bodies. Formation of dust particles and the accretion process. As the nebula continued to spin and compress, the small dust particles began to clump together through collisions and weak gravitational forces, forming larger solid bodies known as planetesimals. These planetesimals ranged in size from a few millimeters to several kilometers and served as the foundation for the formation of planets later on. Formation of protoplanets. The planetesimals in the protoplanetary disk continued to collide and accrete over millions of years, gradually forming protoplanets. In the region near the central core, where temperatures were high, heavier elements and heat-resistant minerals formed rocky planets like Earth and Mars. Farther from the center, where temperatures were lower, volatile compounds such as water, methane, and ammonia froze, forming large gas planets like Jupiter and Saturn. The formation of the Sun. When the central core became hot and dense enough, nuclear fusion reactions began, converting hydrogen into helium and releasing energy. The onset of nuclear fusion marked the birth of the Sun, emitting a vast amount of light and solar wind. The powerful solar wind swept away most of the gas in the protoplanetary disk, reducing the amount of free gas and strongly influencing the planetary formation process around it. The influence of solar wind and chemical reactions. The solar wind swept away the remaining gas and dust in the protoplanetary disk, especially in the region near the Sun. During this process, the rocky planets were strongly affected, which reduced the amount of gas and helped form their first atmospheres. The gas giants, farther from the Sun, were less affected, retaining most of the surrounding gas. The outcome of the solar nebulous stage. After about 10 million years, the nebulous stage ended with the birth of the Sun and the surrounding protoplanets. Collisions between planetesimals and protoplanets generated intense heat, melting part of the surface of the protoplanets and forming their basic geological layers. The planets, including Earth, continued to grow in size and mass due to further collisions with asteroids and other planetesimals. The solar nebulous stage is the first step in the formation of Earth, marking the birth of the Sun and the surrounding planetary system. This process, from the collapse of a cloud of gas and dust to the formation of planetesimals and protoplanets, laid the foundation for the later development of Earth and the other planets in the solar system. Factors such as gravity, collisions, and solar wind played a crucial role in creating the stable and diverse planetary system we have today. Proto-Earth formation stage. The protoplanet formation stage is the phase that follows the formation of a protoplanetary disk from the rotating cloud of gas and dust around the Sun. During this stage, the early Earth, along with other planets, began to form from planetesimals through accretion and collisions, creating protoplanets, large bodies of material capable of eventually forming actual planets. This is a crucial stage, laying the foundation for Earth's physical and chemical structure. The formation and development of planetesimals. After the collapse of the solar nebula and the formation of the protoplanetary disk, dust particles and ice began to collide and stick together, creating small solid bodies known as planetesimals, ranging in size from a few millimeters to several kilometers. These planetesimals formed through forces such as van der Waals forces and electrostatic reactions. The gravitational pull of the planetesimals increased as their size grew, attracting surrounding materials closer, leading to the formation of larger bodies. Accretion and collision process. The planetesimals continued to accrete together due to gravity, forming larger celestial bodies. This process involved numerous collisions, ranging from light impacts to violent crashes that caused fragmentation. In strong collisions, the material bodies could either merge or break apart. However, on average, the collisions helped the bodies grow larger and compact, leading to the formation of protoplanets. Division by distance and material composition. In the protoplanetary disk, regions near the Sun had high temperatures, while regions farther away were cooler. This led to different distributions of materials within the disk. Regions near the Sun, the area of rocky planets like Earth, heat-resistant elements such as iron, nickel, silicon, and other heavy minerals predominated. These elements were less likely to evaporate under high temperatures, so planets closer to the Sun were primarily formed from solid materials, creating dense rocky and metallic crusts. Regions farther from the Sun, the area of giant gas planets, lighter and more volatile materials like water, methane, and ammonia froze and accumulated, forming large gas planets. Formation of proto-Earth. In the region near the Sun, the accretion process of planetesimals and debris continued, forming protoplanets of significant size. During this stage, the proto-Earth began to form through material accumulation. The gravitational pull of the early proto-Earth increased with its mass, attracting more surrounding material. As more planetesimals and debris collided and stuck together, the proto-Earth continued to grow. Heat from collisions. The process of collisions and accretion generated a large amount of heat, causing the early Earth to become fully molten. The high temperatures within the Earth helped separate the elements. Heavier elements like iron sank to form the core, while lighter elements like silicon and oxygen rose to form the crust and mantle. Internal stratification of proto-Earth. The melting of the early proto-Earth triggered a process of differentiation, forming the basic structural layers. Core. The heaviest elements, primarily iron and nickel, sank to the center of the protoplanet and formed the core. The Earth's core later becomes the source of its magnetic field, protecting the Earth's surface from cosmic radiation and solar wind particles. Mantle, lighter elements and compounds such as silicates rose above the core, forming the mantle of the Earth. The mantle has varying thickness and temperature, playing a crucial role in plate tectonics and volcanic activity. Crust, the outermost layer, was formed from lighter elements and compounds, creating the solid crust that surrounds the planet. The crust is where geological activities such as volcanism, earthquakes, and plate tectonics occur. Impact of meteoroids and development process. During this stage, the proto-Earth endured millions of collisions with celestial bodies and meteoroids, especially in the final stages of the solar system's formation, when debris in the protoplanetary disk was still abundant. These collisions not only continued to heat the Earth, but also brought new materials, including water from comets and meteoroids, contributing to the formation of the early oceans and atmosphere. Formation of the primordial atmosphere and oceans. During the process of collisions and differentiation, the proto-Earth released many gases through volcanic eruptions and geothermal activity. These gases accumulated, creating an early atmosphere filled with toxic gases such as CO, methane, and ammonia. As the Earth gradually cooled, water vapor in the atmosphere condensed, forming the primordial oceans. This water came from both chemical reactions within the Earth and from water-bearing celestial bodies. The protoplanetary formation stage is one of the key turning points in Earth's history, when the planet transitioned from a chaotic mass of material into a celestial body with a clear, layered structure consisting of a core, mantle, and crust. The continuous collisions not only provided the heat necessary to melt the Earth, but also brought essential elements for life, such as water. This stage laid the foundation for the complex geological and biological processes that would follow, contributing to the development of a stable planet capable of sustaining life. The early development stage. Formation of the crust and development of stratigraphy. The Earth's crust is a thin outer layer compared to the entire planet, but it plays a crucial role in the development of the living environment and geological processes. The formation of the crust and the development of stratigraphy are the results of many complex geological processes that took billions of years. Below is a detailed analysis of this process. Formation of the primitive crust. After Earth went through the protoplanetary stage, collisions, and differentiation, the surface of the planet was molten and covered by a layer of magma. As Earth gradually cooled, the outermost layer of magma began to solidify, forming the primitive crust. This primitive crust was primarily composed of mafic rocks, such as basalt, containing dense minerals like olivine and pyroxene. These minerals are heat-resistant and formed from solidified materials in the magma. The differentiation between the oceanic crust and continental crust. As Earth gradually cooled, the primitive crust was differentiated into two main types of crust. Oceanic crust. This crust forms from basaltic magma and is dense and thin, with a thickness of about 5-10 kilometers. The oceanic crust is continuously created at mid-ocean ridges, where magma from the mantle rises, cools, and solidifies to form new crust. Continental crust. Unlike the oceanic crust, the continental crust is thicker and contains more felsic granite rock, which is lighter, with an average thickness of about 30-50 kilometers. Granite is a felsic rock, rich in silicon and aluminum, and is less dense than basalt. The formation of the continental crust occurs mainly through plate tectonics and collisions between continental land masses, where lighter minerals accumulate to form large continental blocks. Plate tectonics and the development of stratigraphy. Plate tectonics is the most significant driving force behind the development of Earth's crust. The tectonic plates move due to the influence of convection currents in the mantle, leading to many important geological processes. Mountain formation. When tectonic plates collide, a convergent process, the crust is compressed and pushed upward, forming mountain ranges and high terrain. For example, the Himalayas were formed by the collision between the Indian plate and the Eurasian plate. Ocean trench formation. When two oceanic tectonic plates move apart, a divergent process, magma from the mantle rises, cools, and forms new crust at mid-ocean ridges, such as the Mid-Atlantic Ridge. Volcanic activity. The collision and sliding of tectonic plates can create volcanic regions, where magma from the mantle rises through the crust, forming volcanoes and erupting magma. This is how the Earth's crust is regenerated and new material is added. Formation and development of strata. As layers of material accumulate and form the continental crust, the process of stratification begins. Strata are sedimentary rock layers deposited over time, and each layer carries distinct characteristics from the period of its formation. Sedimentation process. Strata form from rock particles and minerals that have been weathered and eroded from the crust. These particles are transported by wind, water, and ice, and then settle and compact into sedimentary rock layers. Different environments, such as riverbeds, seas, deserts, create various types of strata. Strata layers. Over millions of years, sedimentary rocks continue to accumulate and compact, forming a series of strata. Each layer contains information about the climate, organisms, and environmental conditions of the time it was formed, preserved in the form of fossils and geological traces. Thermal and pressure metamorphism. When strata are buried at greater depths, the temperature and pressure increase, transforming sedimentary rocks into metamorphic rocks such as shale and limestone into marble. Supercontinent tectonic cycles. Throughout Earth's history, continents have continually moved and merged, forming supercontinents that later break apart in cycles lasting hundreds of millions of years. These cycles have contributed to the formation and development of strata and the continental crust. Rodinia supercontinent cycle. Around 1.1 billion years ago, as one of the earliest supercontinents recorded, Rodinia formed through the collision and merging of smaller continents. After existing for several hundred million years, Rodinia broke apart, creating new oceans and coastal regions. Rodinia supercontinent cycle. Around 1.1 billion years ago, as one of the earliest supercontinents recorded, Rodinia formed through the collision and merging of smaller continents. After existing for several hundred million years, Rodinia broke apart, creating new oceans and coastal regions. Pangaea supercontinent cycle. Around 335 million years ago, the most famous supercontinent, Pangaea, formed and existed until about 175 million years ago, before breaking apart and giving rise to the continents we have today. The breakup of Pangaea created conditions that allowed diverse life forms to evolve across the newly formed land masses. Development of continental strata. As continents formed, they continue to undergo various geological processes. Weathering and erosion. Physical, chemical, and biological weathering processes erode the surface rocks, creating new layers of sediment. Climate fluctuations and sea level changes. Climate fluctuations and changes in sea level have a significant impact on the formation and development of strata. High sea levels increase marine sediment layers, while low sea levels lead to the accumulation of terrestrial sediments. The role of strata in geological and climate studies. Strata are crucial evidence that allows scientists to study the evolutionary processes of Earth, climate, and life. The layers of strata store fossils and chemical traces of the climate, the chemical composition of the atmosphere, and even major extinction events. The formation of the crust and the development of strata are the results of geological processes that have taken place over billions of years, from the initial cooling and solidification phase, through the influence of plate tectonics, to weathering, erosion, and sedimentation. Strata not only serve as a record of Earth's history, but also play a crucial role in providing information about climate change, biological evolution, and current geological activities. The emergence of Earth's oceans and atmosphere. The process of ocean and atmosphere formation is one of the most crucial stages in Earth's development history, playing an essential role in creating an environment capable of sustaining life. Both of these elements formed through geological and cosmological events, with complex processes leading to the development of modern ecosystems. Below is a detailed analysis of the formation of the oceans and atmosphere. Primitive atmosphere. During the initial formation stage, Earth was primarily a molten mass, and heavy gases such as hydrogen and helium evaporated into space because the gravity was not strong enough to retain them. However, as Earth gradually cooled, gases like CO, HO, and methane, CH were trapped, forming the primitive atmosphere. Origin of the primitive atmosphere. Earth's initial atmosphere formed through volcanic eruptions, releasing gases from within the planet. These gases included carbon dioxide, water vapor, ammonia, and methane, creating a dense atmosphere rich in greenhouse gases. This atmosphere trapped heat, helping to warm the planet and creating conditions conducive to the later formation of liquid water. Characteristics of the primitive atmosphere. The early atmosphere contained little free oxygen and was primarily composed of gases toxic to most life forms today. However, these gases helped to trap heat, regulating Earth's temperature during the early stages. Formation of the oceans. As Earth cooled, water vapor in the atmosphere began to condense and fall as rain. This condensation process continued over millions of years, forming the initial seas and oceans on the planet's surface. Origin of water. The water on Earth may have two main sources. From Earth, a large amount of water vapor released from volcanic eruptions may have condensed and formed the oceans. From comets and asteroids. Comets and asteroids contain water in the form of ice, and when they collide with Earth, they bring a significant amount of water. Some studies suggest that water from comets and asteroids may have made a substantial contribution to Earth's current water mass. Condensation process. As Earth continued to cool, the water vapor in the atmosphere condensed into heavy rainfall that lasted for millions of years. This massive amount of water began to accumulate in depressions, creating vast bodies of water and forming the primordial oceans. The development of the secondary atmosphere and oceans. After the oceans formed, chemical reactions in the atmosphere and on Earth's surface continued, leading to the development of a secondary atmosphere rich in oxygen and more stable oceans. The process of CO absorption. When the oceans formed, CO from the atmosphere dissolved into the water, forming carbonic acid, which led to the formation of bicarbonate and carbonate ions. These ions combined with calcium in the water to form carbonate minerals, such as limestone, helping to reduce the CO concentration in the atmosphere. The formation of free oxygen. About 2.4 billion years ago, a significant event known as the Great Oxidation Event occurred. Primitive photosynthetic organisms, such as cyanobacteria, began producing oxygen through photosynthesis. This oxygen accumulated in the atmosphere, forming a secondary oxygen-rich atmosphere, which created favorable conditions for the evolution of more complex life forms. The impact of oceans and the atmosphere on the development of life. The formation of oceans and the atmosphere was a necessary condition for the emergence and development of life on Earth. The role of oceans. Oceans provide a stable environment, maintaining temperature and supplying minerals for primitive life forms. Shallow coastal waters create conditions for the development of the first single-celled organisms. In these environments, complex chemical reactions could occur, leading to the formation of organic compounds essential for life. The role of the atmosphere. The initial CO-rich atmosphere helped maintain a stable temperature on the Earth's surface, preventing extreme cold. As oxygen began to accumulate, the ozone layer formed, protecting the Earth's surface from harmful ultraviolet radiation from the sun, allowing living organisms to thrive on the surface. The stability of the atmosphere and oceans. After Earth went through its initial stages of upheaval, the atmosphere and oceans gradually became more stable, creating a sustainable ecosystem. Climate regulation through the carbon cycle. The carbon cycle between the atmosphere and oceans helps regulate the amount of CO in the atmosphere, keeping Earth's temperature from becoming too hot or too cold. This cycle occurs through processes such as the dissolution of CO into the oceans, the formation of carbonate rocks, and the release of CO from volcanic activity. Role of marine organisms. Marine organisms, such as phytoplankton, also play a crucial role in regulating CO levels, as they absorb CO during photosynthesis and release oxygen. When these organisms die, they sink to the ocean floor, storing CO in organic form and reducing the concentration of CO in the atmosphere. Changes in the atmosphere and oceans through the eras. Earth has undergone significant changes in its atmosphere and oceans throughout its history. Climate fluctuations and mass extinctions. Major climate changes and volcanic activity, such as large volcanic eruptions or meteorite impacts, can cause significant disturbances in the atmosphere and oceans. These events often lead to mass extinctions, paving the way for the evolution of new species. The formation of the oceans and atmosphere resulted from cooling processes, the accumulation of water and gases from various sources. Oceans and the atmosphere not only provided a habitat for the earliest organisms, but also played a critical role in regulating the planet's temperature and chemical composition. Climate changes. Geological and biological cycles have all significantly influenced the development of the oceans and atmosphere, thereby impacting the evolution of life on Earth. The emergence and evolution of life. Prebiotic stage. Prebiotic chemistry. Around 3.8 billion years ago, complex chemical reactions in the oceans and surrounding environment produced the first organic compounds. This was a crucial initial step in the formation of living cells. Stage of single-celled life and microorganisms. The first forms of life appeared as bacteria and single-celled microorganisms, thriving in the mineral-rich and organic compound-filled oceans. These organisms absorbed nutrients from their surroundings and, in doing so, produced oxygen, a crucial factor that gradually transformed the atmosphere. Stage of multicellular life and biodiversity. Around 600 million years ago, multicellular life began to emerge and flourish, giving rise to more complex forms of life such as animals, plants, and various other organisms. The Cambrian period, approximately 540 million years ago, is renowned for the Cambrian explosion, a time of rapid emergence of numerous new species. By the Cretaceous period, around 65 million years ago, mammals and other modern organisms began to dominate Earth. Ice ages and climate change. The ice ages are extended periods lasting millions of years, during which Earth's temperature significantly drops, leading to the formation of massive ice sheets over oceans and continents. These ice ages can be divided into major cycles, each typically lasting from several million to tens of millions of years. Timing: Earth has undergone multiple ice ages throughout its geological history, particularly during the Pleistocene epoch, around 2.5 million years ago to 11,700 years ago. The most recent ice age within the Pleistocene, known as the Worm Glaciation in the Northern Hemisphere, ended with the transition to the Holocene epoch, the warmer period in which we currently live. Structure of the Ice Age. During each ice age, vast areas of the North American, European, and Asian continents were covered in ice. These ice sheets could reach thousands of meters in thickness, extending from the poles toward the equator. In other regions, such as Antarctica and Greenland, ice has remained to this day. Causes of the Ice Ages. Many factors have contributed to the formation of ice ages, and these factors interact with each other in a complex cycle. Milankovitch cycles. This is the most widely accepted theory to explain the ice ages. According to this theory, changes in Earth's orbit, axial tilt, and the variation in Earth's rotation, known as Milankovitch cycles, affect the amount of solar energy Earth receives during different periods. These changes either reduce or increase the amount of sunlight reaching different regions of Earth, leading to climate shifts. CO and greenhouse gases. Changes in the concentration of CO and other greenhouse gases in the atmosphere also play a significant role in ice ages. During cold periods, the concentration of CO in the atmosphere decreases, reducing the greenhouse effect and leading to a global temperature drop. Changes in oceans and ocean currents. Changes in ocean currents and global climate systems can create colder conditions in certain regions, altering the climate and causing ice coverage. Changes in the distribution of continents and oceans. The positions of the continents also affect the global climate. For example, when continents are located near the South or North Poles, they can create conditions favorable for the formation of ice and snow. Stages of ice ages. Throughout Earth's history, there have been at least 5 major ice ages, with the 3 most prominent ice ages being Huronian Ice Age, occurring around 2.4 to 2.1 billion years ago. It was the first global ice age. The significant decrease in CO2 due to the photosynthesis of the first microorganisms may have been the main cause of this ice age. Cryogenian Ice Age, around 720 to 635 million years ago. It may have been the most severe ice age, when the Earth was nearly completely covered in ice, a phenomenon known as snowball Earth. During this period, vast ice sheets formed across the polar regions and extended close to the equator. Pleistocene Ice Age. This was the most recent ice age, occurring from about 2.5 million years ago to 11,700 years ago. The Pleistocene Ice Age is divided into smaller cycles with alternating periods of glaciation and warming. Ice ages and climate changes have had a profound impact on Earth's history and life on the planet. Ice ages created harsh living conditions, but also drove the evolution and development of species. Modern climate change, although caused by various factors, is bringing about significant changes in habitats, and like in the past, it will have long-lasting effects on ecosystems and life on Earth. The development of humans and their impact on Earth. Modern humans, Homo sapiens, appeared around 300,000 years ago in Africa. Before that, ancient human species such as Homo habilis, Homo erectus, and Neanderthals existed millions of years ago. These ancient humans gradually developed the ability to use tools, build societies, and develop language. Biological changes, such as the development of larger brains and the ability to control tools, helped humans thrive and adapt to their environments. The development of humanity is not just a story of progress and advancement, but also a story of environmental change and its impact on Earth. Finding sustainable solutions to balance human development with environmental protection is the greatest challenge of the 21st century. In conclusion, the formation and development of Earth is a fascinating journey that spans billions of years. From the fiery chaos of its early days to the stability we experience today, the planet has undergone incredible transformations. The creation of the atmosphere, the formation of oceans, and the rise of life all played key roles in shaping the world we live in. As we continue to explore and understand Earth's history, it reminds us of the delicate balance required to sustain life and the importance of protecting our environment for future generations. Thank you for watching, and remember to keep exploring the wonders of our planet.